Hello, once again. It is Chris Stewart with another weather show for you. And so today we're going to look at the um, situation from KLSX on December 1st, 2018. And what I want to kind of hone in on is a dual polarization perspective from this particular scenario. And so um, what we what's already been pointed out is this is a area of discrete cells that have developed pretty atypical for this time of year, December 1st, and we're going to hone in on the correlation coefficient aspects of these cells and try to make a better analysis of those. So, just a little brief overview of what these dual pole products give us, and it so I'll go to a specific cell here and we'll kind of pick out. Let me find a good cell that we can kind of point out some of these features. And yeah, let's look at this. Let's look at this guy right here. So with any dual pole product, you'll want to keep a reflectivity to compare to. So what I like to do is I like to place a marker in the area that I might be interested in looking at, and then you can also look at the velocity products with that as well. So I have the storm relative velocity set at 216 to 32, but reflectivity is definitely paramount to have with this. And so the first one I'm going to talk about is the differential reflectivity, or ZDR. So this is the ratio of the horizontal and the vertically polarized reflectivity values in a pixel. So if we go down and look at this one, so we can see we have high dBz values here, and we have lower or near zero correlation coefficient values near Clayton. This is Clayton, Illinois. And so what this kind of means is that with hail, we would expect to see a more of a spherical nature in these with hail development, with hailstones. With heavier rain, we would expect to see kind of more of a flat shape. So we would have a higher ratio of the horizontal to the vertical. And then with hail, you'd have a kind of a lower ratio. And so with the ZDR product, you can look at this in combination with the reflectivity product to give you those kind of estimations. And then so up at correlation coefficient, so what correlation coefficient in the top right here tells us is the consistency of the shapes and the sizes of the scatters in the volume scan. So in a precipitation field, how does the joining dual pole, how does the joining scatters compare to one another? So if we could look down here, we have lower values of correlation coefficient, kind of where we see this mass. So this can be as a result of hail, such as hail. So we have lower values. You see a lot of mixing of rain and hail, and where the shapes and sizes of those don't really correlate. So that can also be a good indication. This can also help us identify debris signatures, as well as heavier rain and such. So down in the bottom left is going to be our differential phase shift. So this is a little more of an abstract product for us, but what it basically is the difference in the phase between the horizontal and the vertical caused by attenuation. So if the horizontal is being attenuated more than the vertical, then we're going to have more of it'll show us higher values, and then that's a cumulative over a entire beam. So things like hail is going to attenuate both of those beams really well, and so you'll see this kind of what looks like a spike in attenuation. And so this kind of give you an idea of the maybe how much or how big the hail is. So if stronger attenuation would mean that we have stronger or larger hail fields in that particular area. So Switching this over to KDP, and what KDP shows us is the change in the phase. Let's see if I get this right. So yes, the change in the phase shift difference derived from the differential phase shift. So going back to phi, it is the derived product from phi. It's the change in the differential phase shift. So what this is really good at is kind of picking out areas of heavy rain, and what it really does is also gets rid of any hail parameters. So it kind of takes hail out of the equation and just looks at the heavy rain in a particular scenario. So so that's kind of our introduction to our dual pole products, and now we'll look at some of these, how we can analyze some of these cells with dual pole. And so I'll go back to phi. I like using phi to kind of, you can follow the radial and pinpoint an area where there might be heavy hail, or if you're looking for where you might see heavier hail, then sorry, I was getting a call to turn off my phone. Or where you might suspect that there's heavier hail, you can look at this and see how much hail or how large the hail is in that field with phi. So, so what are we seeing? We're seeing in this cell see, did we already do this one? I think we already did this one. Let's move on to some other cells in the area. So we can see that this guy south of, so we, start to see some 60 dBz value. Ooh, hello. Place a marker here. And what we do notice is that there is some lower correlation coefficients in the middle of this cell. We don't really see much change in the radial, so not much attenuation difference there. And then we do see also correlation or ZDR values near zero. So a little bit of hail in that, not much hail in that field. And then definitely some difference in the precipitation field as far as the sizes go. And we've got a cell that's starting to drop some tornadoes and some funnel clouds. Place a mark on the hail core. Not really noticing much in the way. It's hard to tell with if there's a debris signature within this weak echo region. And so because we're so far away from the radar, you're up at, let's see, how it's like 5,000 feet. I mean, you can still get debris balls that go up to 5,000 feet, but still pretty high up in the air. And then also we have, we're on these are discrete cells. It's hard to pick out an area of lower dBs, lower correlation coefficient, if with say if we have like a debris signature in this area. So not too useful in this case because of all those things I just mentioned. But we do see that there is some relatively lower values of ZDR, and then obviously a lot of drop sorting going on, and some large difference. Once again, though, not a whole lot of change in phi, so it's hard to tell how large that hail core is at that time, as a lot of those parameters aren't really picking up very well. You can see how this changes over time. We'll place a marker here. And so, very, very good correlation with the ZDR, and how that we have kind of a near zero right in the middle of that hail core with the 60 dBz's. And then, of course, correlation coefficients are hard to tell what's going on there because of all the different colors and pixels, but definitely not a whole lot of correlation in the precipitation field for sure in that area. So we can check out storm relative velocity. You can see that there is some rotation, not very strong rotation, more mesocyclonic more than anything else. But once again, we aren't as close to the radar as we'd like to be. So there is a cell. See if we can turn the base reflectivity back on. That is, if this was, I'm not sure if this is the one that caused. Nah, those were from earlier, so that wasn't the one that caused those reports. But you can see that, and it's kind of in the middle of this. There is some. We can go back to KDP as well, and we can check out that this is actually. Here's a good example, place marker here, where you have very, very high KDP values, so heavier rain. You're showing a little bit of a lower correlation coefficient, but not down in that range. And then once again, we're showing flatter, larger drops in this area. So maybe a little bit of hail mixed in there, but for the most part, even with this as strong as the we're kind of well past up that 60 dBs. Let's see if we can get the read at 63 dBz's, 64, 64.5. So strong. What might be hail, but KDP and the differential reflectivity and correlation coefficient. I'll say that this is more likely a lot of heavy rain occurring in this area. So some of the things that can help you identify these features with the dual pole. Yeah. So we'll keep looking at the cells in this area. I won't take up too much more of your time. Oops. And we'll just kind of go toward the last run here, and then because I want to point out some cells that are a little bit closer to the radar that developed. So here's so we're going to kind of hone in. I don't think any of these really had much development. Ugh, my gosh. Yeah, so let's look at this guy right here. This guy that went through Mount Olive, Illinois, and so we noticed that there is kind of what might be a hail core there. KDP is suggesting. We can actually put the place marker here. KDP and the correlation coefficient suggesting this is just an area of heavy rain. Continues to be, oops, oh, it keeps doing that. Place marker here, oops, storm track, place marker here. Again, we're not seeing that near zero in these higher 60 dBz values, and we're seeing strong, some pretty high values in the KDP, and then we can flip it over to phi, and it's showing some attenuation along the radial with that. We'll bring this back over to reflectivity. You can see the storm relative velocity, and we are starting to see some rotation with that. Pretty strong rotation with, see that's about 40 knots, or 40, sorry, that's 40 miles an hour. I've got my scales all jacked up here. Should be looking at knots, but we'll look at it in miles an hour. And then it did drop a tornado with those velocities. And so can we see a debris signature in here? Are we able to pinpoint, so we'll place marker here. Can we see anything in the correlation values? So we do see there's kind of a weak echo region in this area. Stronger hail core starting to develop. So you can see by the lower differential reflectivity, and then also getting lower CC values indicating that. But as far as like where we might see the a debris signature, it's kind of hard to tell, because if we wanted to look at a debris ball, for instance, you would want to see lower correlation coefficient values. And so because we're at the edge of this storm, and because we're still kind of far away from the radar, 3,000, 4,000 feet in the air, we are not really picking up on that feature so much. And we can kind of loop through this a little bit more. Still hard to tell if there is a debris signature in there, because it's so messy in the correlation coefficient values. But definitely some good rotation happening within that. So it'd be enough for me to issue something. And if you go into Tor, of course they don't have anything marked. That definitely starts to pick up in strength. More tornado reports out of this. Still not correlating with a clear debris signature. And we might not get this out of here. This marker here. Yeah. Pretty strong rotation going on now. We're really rock and rolling. And you can see that they got the tornado warning out there. We'll take that away. We'll take the storm. Remove storm track to get some of this stuff out of here. And so, right, I'm going to place a marker here. Still not a whole lot showing us a debris signature in the correlation coefficient. So hard to tell. And that's kind of the challenge of forecasting too, is you have all these products, but you have to kind of be able to tell what is going wrong with them too. And so, because we're at the edge of the storm in this scenario, a pretty good hook echo, probably a bounded weak echo region within that too. So bounded weak echo region. Let's go through the updraft of that. You can see nice hook, good hail core. Place a 1-inch hail. It says it's coming from, but we can place a marker here, and we can see that we have a good lower ZDR values associated with that, and then obviously we're getting some lower KDPs. So it's not heavy rain in that instance, and then also some lower CC values in there as well. But still kind of having a hard time picking out that good debris signature because of the distance, and then the fact that we're on the edge of a storm here. So, but anyway, this is all I have for you today. And if you have anything that you'd like to see, just let me know. All right, Stewart out.